During heavy rainfalls in Peoria, raw sewage can enter directly into the Illinois River from pipes along the riverbank. In the 1980s, about 640 million gallons of untreated water was dumped into the river annually. Corrective measures have reduced that amount today to 180 million gallons per year, far beyond the U.S. EPA limits. While the numbers vary, other cities face similar sanitary problems, including Bloomington. It has open pipes pouring wastewater and pollutants directly into Sugar Creek during high water events.
It's a problem nationwide. This stems from a problem from years gone by in the 1800s when we first started conveying sewage from a point of public health downstream. And invariably it would find a moving waterway because that's what they had.
In those early years, plumbing and industrial waste was carried in the same pipes as stormwater. Thus, the pipes were called combined sewers. The sewage entered nearby streams and rivers through pipe openings along the banks. Many of them are still active today. The public may not be cognizant of them, mostly because they are out of sight. However, leaders of cities and wastewater treatment plants are fully aware, as they face millions of dollars in upgrades to their sewer systems. Cities have made improvements in the intervening years. Starting in the 1920s, wastewater treatment plants were built to clean wastewater before returning it to rivers. As cities expanded, they installed separate pipes for rainwater and wastewater, but the combined sewers remained in older areas. When there was too much rain, the system could not adequately handle the large flow, and excess effluent poured into waterways.
Those combined sewer overflows, as they're called, are regulated by the EPA. We have to have a permit in order to operate those. Over time, the EPA, through the Clean Water Act and so forth, has been mandating that combined sewer overflows, if they're very active, that something be done to make them less active or go away.
The town of Normal and the Bloomington-Normal Water Reclamation District also had combined sewers. Normal already closed its 2 overflow outlets, but Bloomington has sites at Locust and Maysfield Streets. The one at Locust is a combined sewer running diagonally under a field next to Bloomington High School.
That really is sized as a storm sewer, so let's get all the sanitary services out of it, provide a new sanitary sewer, and use this pipe as a storm sewer, and we'll build a new smaller sanitary sewer, and we'll be able to separate that neighborhood.
Work has begun at the Maysfield location, but the city hasn't developed a complete solution to limit discharges into Goose Creek during heavy rains.
We've had some inlets that we were able to, stormwater inlets that we were able to move to storm sewer, and we're monitoring things as we can separate some stuff, just monitoring to see if that reduces the CSO activity even more.
The Water Reclamation District was able to close some combined sewer outlets after the 2007 construction of a lagoon to retain large amounts of sewage.
We partnered with the city of Bloomington when this property became available to put a 90 million gallon lagoon that's behind us and the infrastructure to bring the water that normally would discharge into the creek to this lagoon. Behind me you can see 3 10 by 10 flap gates right near the surface of the water. And those flap gates can deliver a rate of 700 million gallons a day to this lagoon. There are 3 36-inch pipes up on the embankment behind me. Those are connected to 3 large propeller pumps. They also deliver water to this lagoon. As the lagoon fills, the gravity flow into the lagoon will decrease because the head on the lagoon is getting higher and higher. So we have to supplement that and take over the flow with large pumps.
The lagoon acts as a holding tank, storing overflow until the treatment plant can catch up after a storm. Bloomington hopes to resolve the CSO issue by 2030. Corrective steps in Peoria aren't expected to be finished until 2039. The Greater Peoria Sanitary District owns a large majority of the city's sewers, all of which are separate storm and sanitary sewers. It doesn't own the combined ones located in the oldest parts of the city.
The combined sewer system is one of those sewer systems the city of Peoria still owns. So think of the combined sewer area as being downtown Peoria up to Spring Street, but then also to the other way down to Darsh Street.
Efforts to limit the number of overflows have been underway for decades. An early project was the construction of an interceptor, which collects wastewater from other sewer lines. It is the largest pipe, with a diameter reaching 8 feet as it approaches the treatment plant in South Peoria.
And what we essentially did early on was build the interceptor sewer, the riverfront interceptor, which runs about 5.5 miles from the treatment plant here, all the way up the Illinois River, close to the Route 150 bridge.
Today, there are 2 interceptors, the Kickapoo, shown in red, and the Riverfront Interceptor in black, both ending at the treatment plant. Small sewer lines from homes and businesses eventually connect to trunk sewers, shown in blue, which then feed the interceptors.
The U.S. Environmental Protection Agency reached out in the early 80s to the city of Peoria and said that we were in violation of the Clean Water Act. At that point in time, the city did a number of, and the sanitary district did a number of infrastructure improvements to the system in order to be able to comply with the federal government's Clean Water Act.
One improvement was the aptly named Swirl Building, located at the foot of the Murray-Baker Bridge, to help meet the Clean Water Act regulations.
When it starts to rain, that building and those structures also function as first storage in nature to capture those smaller storms. But then, if the storms are of such magnitude and are of such a size that they tend to overflow, those buildings use the centrifugal nature of the water flow to capture all the solids that might be in wastewater, direct those to the treatment plant, so that primarily what goes into the river at that point would be primarily stormwater in nature. That worked well for a few years, and then in 1994, the United States EPA changes the rules again and results in a series of decade-long negotiation that's finally been resolved, and moving into the future, how Peoria and GPSD are going to ultimately comply with the new regulations.
In order for more of the combined sewer flow to reach the sanitary district's treatment plant rather than the river, the district will invest in some new gray infrastructure. That will require larger concrete trunk lines going into the riverfront interceptor.
There's excess capacity in the riverfront interceptor when there may be overflow events. So if we can increase the size of the piping that leads to the interceptor, you're going to capture more sewage and more rainwater into the interceptor before there's an overflow event into the river. With modern technology, you have gates called control gates that can measure the level in the interceptor in real time and tell the regulator to send more water or send less water depending on the rain event, where it's happening, and the intensity of the rainfall. So if you can make the diversion structure larger and make the connector pipe from that regulator to the interceptor larger, you're going to capture more water.
The city of South Bend, Indiana, faces a similar issue.
Because everything's underground and it's dark to us, we just didn't have a good idea how much flow was in a sewer. So was a sewer a third of the way full, or was it halfway full, or was it almost full?
To reduce the number of overflows into the St. Joseph River, the city first used a traditional approach by separating some combined sewers in 6 neighborhoods. It then took an innovative step in partnering with a private company to put 150 sensors into the sewers, accessible beneath manhole covers. The sensors monitor water level, flow, and other characteristics which can be read at one of numerous control cabinets, or at the city-owned water treatment plant, or from anywhere in the world through an online portal. The system is designed with 3 purposes or layers. The first layer measures the level and flow rate in the sewer. Luis Montestruque founded the company that partnered with the city to develop the first of its kind sensor system.
The second layer is what we call the digital twin, which is the part where we simulate how the system will behave utilizing machine learning, and we can forecast what the system will do. And the third phase is the control, is where we utilize the sensing and the digital twin to then route water so that we can avoid overflows.
Prior to the development of the sensors, South Bend's plan included the construction of as many as 9 huge concrete tanks beneath parks and other sites throughout the city. The tanks would hold storm and wastewater until the treatment plant could process it.
With the knowledge we've been able to gain with the modeling from the sensors placed within our system, we were able to identify that many of the tanks in our original plan were just simply not needed. And so where we thought we needed to store, we needed to capture water, it really wasn't necessary. Our pipes had more capacity than we understood. There were ways for the water to be moved throughout the system in which we could utilize capacity that wasn't being utilized at the time. Now we can, and that's the beauty of smart sensors.
The construction of some parallel sewer lines, upgrades at the wastewater treatment plant, and installation of sensors has already been completed at a cost of $150 million. It's the first phase of the city's efforts to limit overflow into the St. Joseph River. Phase 2 will include what will now be only 4 tanks. While they may be near open spaces like Memorial Park along the river, they'll be underground and not interfere with accessibility to them.
For the most part, it's adding some big tanks that instead of overflowing to the river, they'll overflow to the tank. The tank will hold it and put it back in the interceptor once it stops raining. Or if there's too much flow and it's got to overflow, at least it'll have some partial treatment because we'll be able to get rid of some of the floatables and we'll be able to do some disinfection there so there's not as much E. coli going to the river.
Water flows into the city's water treatment plant and remaining pieces of debris are removed here. The treatment process begins afterward. The original Phase 2 approved by the U.S. EPA was estimated to cost an additional $713 million. City leaders felt that placed too much of a financial burden on city residents.
When you have a plan that you can't afford, you really have no plan at all. So that's where we were in South Bend. We had no plan at all because when we were going to spend $10,000 per man, woman and child, not just per, employed adult or anything like that, but per man, woman and child here, $1 billion plan. Say $1 billion because it was $863 million plus the financing cost of that.
The city used the data collected from the smart sensors to demonstrate to the EPA there could be fewer overflow events while spending less money. Before sensors were employed, the city discharged 45 million gallons of overflow directly into the river during each 1-inch rainfall. That has now been reduced.
85% of our long-term control plan has yet to be built. And last year, 1 inch of rainfall was the equivalent of, or resulted in, between 5 and 6 million gallons of CSO. So we were able to say, well, we've done this without actually building the grey infrastructure.
The new plan does not call for the city to close any of its 35 overflow pipes. EPA regulations don't require elimination of overflows from these outfalls, but instead to limit their frequency, generally to fewer than 3 discharges per year. The new agreement reduces the cost of Phase 2 by 60%, saving the city $437 million. While South Bend's plan largely involves sensor technology and gray infrastructure, it also includes a smaller amount of green infrastructure, like bioswales and permeable pavers.
At present, the city's had pretty good experience with permeable pavers. We've done quite a few streetscape projects in which we've incorporated permeable pavers and we've had great success. So that's always an opportunity that we'll be considering.
The best solution is the one that has a fewest moving parts kind of thing. So that's why we kind of favoured things like downspout disconnection, simple bioswales, anywhere to detain water on its ultimate route to the river.
There are challenges with green stormwater infrastructure. There is the ongoing operations and maintenance of the project. However, We're excited. We think that green has a place in our plan.
Green infrastructure is currently the primary method the City of Peoria is using to address its combined sewer overflow issue. But green wasn't a part of early approaches. The cost of a sewer separation plan in the late 1920s was pegged at $6 million, and the cost of a similar project in the early 1950s was estimated to be $16 million. Peoria leaders rejected both plans. But they did support a 1990s proposition presented to the U.S. EPA.
The original proposal that we presented to them was a series of tanks along the Illinois River that would hold the sewage until we could then safely discharge it back into the riverfront interceptor. That proposal that the city prepared was about $90 million, and that was rejected by the U.S. EPA. What the EPA wanted us to do was to put together a large new pipe that would capture all of that sewage, run it down to the sewage treatment plant. That cost of that pipe would have been $500 million for the city to do that. And there's no U.S. companies that do that work. We'd have to bring somebody in from out of the country to do that kind of boring and to do that kind of infrastructure work. Fast forward now to the early part of this century, and we received notice from the EPA, it was I think in 2005, where they said that we were still, our long-term control plan, which is our plan for managing sewage in the city, was not being approved by them, that we were still in violation of the Federal Clean Water Act. And that started nearly a 12-year process or 15-year process of negotiating with the federal government over a revised consent decree in order for us to make the improvements to the system and to get down to virtually no discharges of sewage into the Illinois River.
EPA approval of projects has been oriented toward communities like South Bend that are using mostly gray infrastructure. Peoria faced difficulties getting approval because nearly 2/3 of its innovative plan involves green infrastructure. To show the EPA a green solution can work in Peoria, the city studied soil infiltration rates and then built a demonstration project along several blocks of Southwest Adams Street.
That native soil that was there was, in many cases, like beach sand. I mean, you were getting well over 6 inches per hour without hardly any excavating of any existing material at all. So, as you stay below the bluff and as you're closer to the river, we're anticipating typically seeing those better infiltrating soils. So that was a demonstration project that helped EPA buy into the fact that these soils will infiltrate water and in green infrastructure can be cost effective.
The consent decree with the EPA affects all the city's combined sewers shown in blue. It's approximately 8 of the city's 50 square miles. It stretches along the Illinois River from near the I-474 bridge on the south to its northernmost reach where it borders Glen Oak Park. The area shaded in tan is above the bluff, and the green area is below the bluff.
We look at our topography, we look at our soils here in Peoria, and we said, we are a prime candidate for implementing within our consent decree the green stormwater infrastructure solutions. We have very sandy soils below the bluff. We can infiltrate water very quickly in this part of the city.
We have areas that are very sandy and infiltrate extremely well, but then we can go a few hundred feet and we're into clay soils that don't infiltrate as well. So strategically, we're trying to make sure that we're utilizing those high infiltrating areas because that's what's cost effective.
Infiltration tests with units like this have verified the permeability of soil under the streets. Where tests show the native soil won't meet required infiltration rates, crews will substitute different, more permeable soil.
What we'll be doing then is we'll be excavating probably 4 feet below that, and then we'll be putting sandy soils back in there that'll infiltrate, well and above our target goal for the native material was like a 4 inch per hour. Well, this 4 feet of material we'll put in there will infiltrate better than that.
And in some cases where impenetrable clay is underneath one side of a street and sandy soil is beneath the other side, pipes will carry water under the street from the dense clay to the sandier soil. To maintain aesthetic features, both sides of the street will appear the same on the surface. The consent decree includes performance milestones the city must meet. During the 18 years of construction, the project is expected to reduce both the number of overflow events and the volume of discharge into the river at years 4, 7, 10, and 14. In the final 4 years of the 18-year project, gray infrastructure may be used in areas that need additional remediation based on the success of the green infrastructure. The first year's construction is a 20 square block area in the North Valley. It is roughly bordered by Adams Street near the river and Glendale Avenue close to the bluff, and from Spring Street on the south to Cornhill Street near the school district's Woodruff Career and Technical Center. On streets running perpendicular to the river, the city will use permeable blocks along both sides of the street. Water will infiltrate between the joints to reach the soil below.
And these pavers are about the size of a concrete block. They're not tiny little bricks, so they're larger. There's not aggregate in between them, so there's little knobs on the end that will let the water infiltrate through those. So that's going to get the water through the block super fast.
A sensor sits below some of the blocks to confirm permeability and to monitor when the crevices between the blocks should be cleaned.
They'll have to be cleaned every once in a while. The vendor that we're working with, they have had great success with this though. So one of the differences is that these blocks don't require sand in between them to keep it at a structural solid surface. So we are just vacuuming ours out every once in a while.
Sensors are also in some sewer lines and at the outfall sites to measure flow and depth of any water reaching the river. In year 1, on streets that run parallel to the Illinois River, the city will construct bump outs at intersections, like those at the demonstration project on Southwest Adams. Inlets will allow water to flow through an underground pipe to the subsurface of the permeable pavement. The bump outs are designed with consideration for how street sweepers and snowplows are able to navigate the curvature of the curbs.
So when they did the Adams Street project, they actually brought down a street sweeper and had it make the turns on the street, and they painted out the radius so that they could incorporate that into their design so that we could be able to maintain those locations.
The Adams Street project established another benefit to using green infrastructure. While no U.S.-based contractors have the current ability to construct deep tunnels, local contractors can provide green solutions.
This way we can create new businesses, so there'll be new need for contractors who can build green infrastructure and maintain green infrastructure. Green infrastructure is also something that will be a lot of times above ground, where the community can see where their money is going, as compared to a deep tank or tunnel that's underground that no one sees and has no connection to.
Part of the solution is to keep stormwater from reaching sewers in the first place. South Bend has swales in several of its parks with plants that have deeper roots to absorb water. Peoria created an urban stormwater farm called the Well Farm at Voris Field, a few blocks west of the Peoria Chiefs ballpark. Poplar trees were planted because their root systems grow quickly.
So the purpose of the Voris Well Farm is to create a stormwater management feature with an urban forest. So there's all sorts of monitoring in place so that they can see the difference between where those trees are planted and the stormwater runoff.
The city of Peoria has allotted 2% of the overall CSO cost, or about $2 million annually, to maintain the improvements once they're completed. But it will take more than just a city's efforts to reduce the amount of sewage flowing into the Illinois River during heavy rainfalls.
A private citizen can do what we've done. You're standing in front of the Department of Public Works administrative offices, one behind you and one here where you see a rain garden. All of these plants are known to take higher volumes of water. And again, various species take on various volumes of water.
Lawn turf grass that we use has very, very shallow roots, only a couple inches. And every time you cut, as tall as it is on the top, that's how deep the roots are. So it doesn't absorb a lot of water. If you think of trees or shrubs or native plants that are adapted to being in a prairie, they have deeper roots and they can absorb more of that water so that it doesn't just run off into the street.
Even with citizen efforts, the cost of mitigating combined sewer overflows is substantial, whether it's a green or gray solution. Peoria will spend more than $100 million, and South Bend more than $400 million. As in any city, the cost is borne by homeowners.
The residents get a utility bill every month that includes their water utility and their wastewater utility, and that wastewater utility charge, part of that goes to help pay for the long-term control plan. Other parts help for the ongoing operation and maintenance of our existing system. But every dollar that we spent on the long-term control plan was going to be paid for by those utility ratepayers.
And the cost in Peoria is covered in a similar manner. Sometimes, society must pay today to correct actions of the past. More than a century ago, it was the construction of combined sewers. Today, it's the cost of cleanliness.